We are back. Let's get down to business and jump right into the second way of formulating a hypothesis, which is inductive reasoning. Inductive reasoning follows a style that is opposite to deductive reasoning. Here, you make a statement that moves from a specific to a general event. This means that it uses a specific observation to create a general principle. Let's look at an example to understand this well. Since the inductive reasoning starts from an if statement, it will be read like, if we know that sparrows have wings and they are birds, and we know that eagle, parrot, hawk, crows are birds too, then we conclude that all birds have wings. Did you see how we started from a specific bird, sparrow, and ended up with a general statement representing all the birds? That's how inductive reasoning is done. And science often uses this method to generalize the information from specific events. In short, inductive and deductive reasoning are two very popular methods that a biologist uses for creating a hypothesis. But there are other ways too. Have you heard this before? What is now proved was once only imagined. This is a known quote by William Blake. So, intuition or imagination is one of those other ways. Next up is aesthetic preference, along with religious or philosophical ideas that also help scientists in making a hypothesis. Comparison and analogy with other processes have shown some progress as well. And finally, the discovery of one thing while you were actually looking for another has helped too. All of these ways can also sometimes form bases for a scientific hypothesis. But the journey doesn't end here. Hypotheses are subjected to rigorous testing, and scientists run repeated tests to prove each hypothesis. What do you think could be the purpose of multiple tests on just one hypothesis? Well, firstly, it avoids any false results. Then, it increases the scientist's confidence in the hypothesis. Also, any hypothesis that is tested repeatedly without proven false is considered well supported and is generally accepted. In fact, this hypothesis can be now used in formulating further, newer hypotheses. Wow, that would certainly lead to many new discoveries. So, when a hypothesis gives you a series of positive results and is supported by all kinds of tests, it then becomes a theory. But how do scientists know if their theory is good? Well, a good theory is predictive and has explanatory power. It can also suggest new and different hypotheses that science can further test. A theory of this kind is therefore marked as productive. And in order to make it extra productive, the testing still goes on. Many ambitious scientists take a hard challenge to disprove newly found theories. Don't you think it's strange? Who would like to disprove an already proven hypothesis? But it happens because scientists have to be absolutely sure that the theory can stand the test of time. So, if a theory survives this skeptical approach and is backed up by experimental evidence, it becomes a scientific law. Like the Newton's law of motion, law of gravity, and law of momentum, or the Hardy-Weinberg law or Mendel's law of inheritance. Wow, that's a perfect treat for a biologist's hard work, I must say. So, how do we define a scientific law? A scientific law is a constant fact of nature that cannot be refuted or disapproved. Obviously, who would refuse such a law that has passed such crucial hurdles? So, the laws made in this way are more general and broader than theories. It can give answers to more complex questions. That's why in biology, you see fewer laws than theories. It's also because nature is quite elusive, as it hasn't been discovered completely and is forever evolving. But thanks to this unique, powerful, and very logical biological method of producing theories and laws, we get updated and authentic knowledge. One day, if you become a biologist, you will be using these several steps of a biological method too. Or who knows, maybe you bring something new to the table.